I'd like to begin by giving us at least a working definition of a set. For our purposes, a set is simply going to be a collection of objects. For example, suppose I wanted to talk about the set of seasons. We have spring, summer, fall, and winter. Notice that I've written them in a certain way. They have commas between them and they're enclosed in braces. That is standard set notation. The objects are separated with commas and enclosed in braces. We can also give the set a name so that it's easier to refer to it. So I might call that set S. Reminds me of the word season. Each object in a set is called an element of the set. So this particular set has 4 elements. Also, there's a standard notation for indicating the number of elements in a set. And this is what we would say using the above as an example. Use the small letter N and then put the name of the set in parentheses. So we would read this: the number of elements in set S is equal to 4. Let's just look at a few more examples. I could say the set consisting of the elements 1, 2, 3, 4, and 5 is a set, and I might give it a name. I just called it T. It could be anything. I could have a set U, which is 1, 2, 3. Now when you see the dot, 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 the ellipses, that means the pattern continues just the same way. So we've got consecutive integers here. So it's 1, 2, 3, 4, 5, 6, 7. Keep on until you reach the last number listed, which is 1,000. So those would be the first 1,000 counting numbers, if you wanted to think of it that way. I might have a set V. Notice it's a little different than U. There is no last number listed. There are ellipses, which means the pattern continues, but there's no end. So this means this continues infinitely. So it's 1, 2, 3, 4, 5, 6, and it just keeps going. Those would be the set of counting numbers, if you wanted to think of it that way. This set W is a little different. This is written in something called set builder notation. And here's how you read it. The set of all X, such that X is a 2-legged animal. Now, the opening brace is read as the set of, and then you have all X. The colon is read as such that. So whenever you see that colon, you read it as such that. That's the colon. And then whatever the condition is, X is a 2-legged animal. So that would be the set of 2-legged animals. For example, a chicken would be in that set because it's a 2-legged animal. A dog would not be in that set because it's not a 2-legged animal, and so forth. So those are just some simple examples of sets. We can also talk about a concept of a set being well defined. Now, by definition, a set is well defined if it's possible to definitively determine whether or not a particular object is a member of the set. So you look at any object and you can decide definitively whether it's in that set or not. I'm going to show you 2 examples and let you see what you think. The first is the set I call A, which is the set 1, 2, 3, 4, 5. Now I don't know about you, but I can't think of a more well-defined set. I definitely know 1 is in A, 7 for instance is not. 2 is in A, 45 is definitely not. 3 is in A, 1/2 is not, and so on. So that is a perfectly well-defined set. Set B is somewhat different. Set B is written in set builder notation, and it said B is the set of all X, that's it. X is tall. Well, that can't possibly be well defined without saying what tall is. What I consider to be tall might not be what you consider to be tall. So that would be a simple example of a well-defined versus a not well-defined set. And that's really pretty much the extent that you need to know about that. It's a fairly common sense idea, at least to the extent that we'll be using it. Now I want to talk a little bit about symbols. I've introduced some symbols already. Here's another one we'll use a lot. This symbol, which to me sort of looks like a pitchfork, or the Greek letter epsilon, is the symbol for is an element of. We'll be using that a lot. For example, if I go back to that set A, which is the set of numbers 1, 2, 3, 4, and 5, then I could say, for instance, that 2 is an element of A, because 2 is an object in that set, or an element in that set. Now, in general, when we write something is not something, we simply take a diagonal line and put it through the symbol for it being that. So the standard way of saying that something is not an element of a set would be to write that diagonal line slash through the symbol for is an element of. And you would read that 7 is not an element of A. We also talk about something called the empty set. The set containing no elements at all is called the empty set. Sometimes it's called the null set. There are tons of examples you could make up, but I'll make up this simple example. If I say let M be the set of all X such that X is a female U.S. president before 2010, as you probably well know, the United States has never had a U.S. president that's female yet, so that would be an example of the empty set. Since that set is empty, we could write it either, and here's our notation, the empty set can be written two different ways, two common ways of writing it. A circle with a diagonal slash through it, or a set of braces with nothing in it. Those are both common symbols for the empty set. So the empty set is often written this way, and it's often written this way. You don't have to write both, but either symbol will do, and they both mean the same thing. Now let's look at a set that's essentially the opposite of the empty set. The universal set is the set of all elements under consideration for a particular problem, and we usually use a capital U to stand for it. And probably the easiest thing is just to look at some examples. Suppose I'm choosing a 3-person committee from the 50 members of some club. Then the universal set will be the names of all 50 of those members. I'm not going to pick a person for that committee who is not in the club, so a person's name who's not in the club would never appear in the universal set. By the same token, I want the possibility of choosing any of those 50 members, so all of their names should appear there. So the universal set would simply be the set of 50 names of the members in that club. Another example. Suppose I'm looking at course grades in a class where the only grades you can get are A, B, C, D, F, and W for withdrawal. If those are the only possible grades, then the universal set would consist of A, B, C, D, F, and W. Those are the only possibilities, so they're the only things that go into the universal set. Third possibility, third example. Suppose I'm rolling a die, just an ordinary die with 1 through 6 on the sides, and I'm going to roll it twice, and I'm going to count how many 5s I get. Well, what are the possibilities? Well, I could roll it twice and I get a single 5, so that would be 0 5s. I could roll it twice and only get 1 5. I could roll twice and get 5 both times. But I can't roll 5 3 times because I'm only rolling the die twice. So the universal set would simply consist of the numbers 0, 1, and 2. And the big thing you probably should get out of all these examples is this. The universal set is contextual. It depends totally on the context of the problem.